All right. So, since all stars fuse hydrogen into helium at some point in their life, that actually is one of the largest ways to release energy through fusion, fusing hydrogen into helium. Turns out that as we get closer and closer to fusing iron, there's less and less energy released from those elements. But there's a balance right now happening in our sun between the amount of fusion and gravity, because it's happening at a consistent and constant rate, the fusion, right? And gravity, of course, because the mass of the sun is remaining generally the same, the amount of gravity on it remains constant. So it stays nice and balanced until the end of its life, where it becomes a red giant, and then eventually the core remains as a white dwarf, while the outer part just kind of gets lost into space. All right, so let's talk about supermassive stars, or just massive stars. So massive stars are able to fuse elements other than just helium, right? So hydrogen into helium. And sometimes other smaller stars will fuse helium into oxygen and carbon at the end of their lives. But massive stars are able to do more than that. They're able to fuse things all the way up to iron. And iron is the most stable element. And actually, when you fuse it, it doesn't really release, it releases very little energy at all. It almost takes in the energy. So it's like a nice balance. So iron is the most stable element, therefore it is at the center of massive stars' cores at the end of their life. All right, so here's a little bit of information. When we fuse hydrogen into helium, we release a tremendous amount of energy. That's why it's super high. When we fuse helium into carbon and oxygen, we release a little bit less energy. And eventually, as we fuse heavier elements like nitrogen and neon, we eventually fuse them into iron, which releases the least amount of energy. Once we get to iron, now when we get to heavier elements, they actually absorb energy during fusion. So they need to take in energy. While these end up releasing energy or giving off energy when they fuse, these elements over here take in energy while they fuse. So they need a tremendous amount of force and a tremendous amount of heat and pressure in order to fuse and to come into existence, like lead, gold, silver, uranium, what else, like platinum, stuff like that. Okay? So these things actually give off energy when we split them, right? The heavier elements. The lighter elements give off energy when we fuse them. And stars are only fusing things. Stars are not fizzing or splitting elements. They're only fusing them. And this has a big impact on the end of a massive star's life. So think about it. Hydrogen fusing into helium releases a lot of energy, but eventually we get to the point where iron forms and it's not releasing energy. So what happens is that at the end of a massive star's life, it really starts fusing a lot of iron elements, which makes its core cool down, right? If we're not giving off energy, then we're not producing heat. So the inside of this star begins to cool down. And when we cool down the inside of a star, the fusion or the outward pressure decreases, causing the star to collapse. And that's the entire outer part collapses in towards the center of the star due to gravity. All right? So, massive stars are like onions, fusing more and more dense elements until we get to the core where there's mostly iron and nickel. All right? So, all of these elements, a lot of these elements, make up who you are. You have copper and oxygen in your body. You have hydrogen in your body. You have iron in your body. You have some sulfur. You have some silica, right? You have a little bit of all these different elements. And it's interesting that the universe began as hydrogen, helium, and lithium, and now we have all these other elements. So, main idea is that the atoms in your body, the iron, the oxygen, the carbon, all formed inside of stars. And then when they exploded, those elements went throughout the universe, eventually became a solar system, our solar system. Parts of that became Earth, and then parts of us came from Earth. So you are made of the remnants or the little bits of old dead stars. So you're made of stardust. Sounds crazy, but it's true. Okay, the end of a star's life. Most massive stars become super red or red supergiants, or blue supergiants or white supergiants, but mostly red supergiants. And when the iron forms, remember, it doesn't release much energy, so the outside of the star begins to collapse because there's not much heat being given off. And then when it collapses in, it eventually crushes the inside of the star, forcing electrons and protons to combine to form neutrons. And sometimes that will explode outward, right? So that will explode outward as a supernova to form either a neutron star or a black hole, okay? So that's the general idea behind the end of a massive star's life. And this becomes a nebula. So when we see a round nebula like this, we know that at the center of that used to be a supermassive star that has gone supernova and exploded outward, carrying these new elements, these heavier elements, heavier than hydrogen, helium, and lithium, out into space, and eventually forming other solar systems. So, what happens is, at the end of a supermassive star's life, when the core collapses and the outer part crushes in on it, it forces, like I said, the protons and the electrons to touch. And when they touch, they form neutrons. Neutrons are not like electrons and protons. Electrons and protons don't want to be near each other, right? Just like how protons don't want to be really be near protons, electrons don't really want to be near electrons. But neutrons don't really care because they're neutral. So they could stack really, really close to each other. Okay? So atoms are actually mostly empty space. Their protons are in their center while their electrons are on the outside. But what's between them is literally emptiness, nothingness, right? What happens with neutrons is if we stack up a bunch of neutrons, they could form a really, really dense ball. A ball so dense that if I had a ball of neutrons the size of like a bigger, like kind of a big marble or a ping pong, it would weigh the same as the Empire State Building, but it would be that big. So we turn these massive stars that are like the size of Earth's orbit almost into these small Earth-sized neutron stars that spin really, 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 really fast sometimes, okay? But if we have a star that's massive enough, we'll skip the neutron star and it'll go right into a black hole, which just means those neutrons that form actually collapse in on themselves, really tearing a hole through space and tearing a hole through time and forming this infinitely dense mass called a black hole, okay? That not even light can escape out of. And we'll be talking more about that, but this is a real picture of a black hole. This is really what it would look like from an artist's rendition. And this is what a black hole does to space itself. It completely warps space. All right? So we'll talk more about this, and then we'll move into the end of black holes.